Imagine a world completely different from our own, where the rules of physics as we know them cease to apply. This is the quantum realm, a strange and fascinating place where particles behave in ways that seem impossible according to our everyday experiences. In this hidden world, things aren't quite so clear-cut. They exist in a haze of probability and potential. Just as we perceive a world of solid objects, the quantum realm operates on scales so tiny that they are beyond the reach of even our most powerful microscopes. To understand the quantum realm, we need to shrink ourselves down to the size of atoms and even smaller, to the realm of subatomic particles. This is where quantum physics comes in, a branch of physics that attempts to explain the behavior of matter and energy at this fundamental level. It's a world where particles can be in multiple places at once, where they can tunnel through walls, and where the very act of observing them changes their state. In the quantum realm, we encounter the building blocks of everything around us, particles like electrons, photons, and quarks. These particles don't always behave like tiny balls of matter, as we might imagine. Instead, they exhibit strange and counterintuitive properties. One of the most mind-boggling concepts in quantum physics is the idea that particles can also behave like waves. Imagine a tiny marble rolling towards two slits in a wall. In our everyday world, we'd expect the marble to go through one slit or the other. However, in the quantum realm, particles can act like waves that spread out and pass through both slits simultaneously. This wave-particle duality, as it's called, is a fundamental aspect of quantum mechanics and has been demonstrated in numerous experiments. The most famous demonstration of wave-particle duality is the double-slit experiment, first conducted with light in the early 19th century, and later repeated with electrons and other particles. In this experiment, particles are fired at a barrier with two slits, and instead of hitting the screen behind the slits in two distinct bands, they create an interference pattern, much like what we see with waves. This interference pattern arises because the wave associated with each particle passes through both slits simultaneously, interferes with itself, and creates a pattern of bright and dark regions on the screen. The double-slit experiment beautifully illustrates the wave-particle duality of matter, showing that particles can exhibit both wave-like and particle-like behavior. It's as if the particles themselves don't decide which slit to go through until they are observed on the other side. This strange phenomenon is one of the many examples of how the quantum realm challenges our classical intuitions about how the world works. In our macroscopic classical world, we can predict the trajectory of a ball or the speed of a car with a high degree of accuracy. However, in the quantum realm, things are much fuzzier. The act of measuring a quantum particle's properties, such as its position or momentum, inherently affects the state of the particle. This means we can never know both a particle's position and momentum with perfect accuracy at the same time, a principle known as Heisenberg's uncertainty principle. This fundamental limit on our ability to measure quantum systems is another key distinction between the classical and quantum worlds. The implications of quantum physics extend far beyond the realm of theoretical physics. Technologies like lasers, transistors, and magnetic resonance imaging, MRI, all rely on principles of quantum mechanics. As we delve deeper into the quantum realm, we unlock new possibilities for technological advancement, potentially revolutionizing fields like computing, medicine, and materials science.